Hi, this is Shifra Chatterjee. Welcome to my Math News channel on YouTube, where I explore the use of mathematics in art. In the last video, we looked at the works of Helaman Ferguson. In this video, I'm going to look at the works of George W Hart, another leading mathematical sculptor who specializes in geometric sculptures. George W Hart is a prolific sculptor and geometer who holds a BS in mathematics from MIT, an MA in linguistics from Indiana University, and a PhD in electrical engineering and computer science from MIT. He is known for his geometric sculptures. Over 100 of his sculptures are on public display around the world. So now, let us look at one of his many beautiful sculptures, the Sierpinski Tetrahedron. To understand this work better, let us first look at the Sierpinski Triangle. The Sierpinski Triangle is a shape based on fractal geometry. It can be constructed from an equilateral triangle through repeated removal of triangular subsets. Here, in the first step, the first equilateral triangle is broken into 4 smaller equilateral triangles, and then the one in the center is removed. In the second step, this process is repeated for the 3 triangles in black. And this process can be repeated any number of times to yield Sierpinski triangles of increasingly higher orders. The Sierpinski tetrahedron is a 3-dimensional generalization of the 2-dimensional Sierpinski triangle. Note that the holes created in the Sierpinski tetrahedron by the removal process are octahedrons, a Platonic polyhedron with 8 sides, each of whose faces is an equilateral triangle. The picture here shows a 5th order version, as there are 5 different sizes of octahedral holes: 1, 2, 3, 4, and 5. This model is scaled, so the tetrahedron edge is about 8.5 inches long. It is 3D printed in nylon polyamide by selective laser sintering. Let us now look at one of George Hart's favorite sculptures, the rose Untaken. It is based on the icosahedron, which is a Platonic solid with 20 faces, and each face is an equilateral triangle. This beautiful sculpture invites contemplation and poses many interesting mathematical questions. Note the light roads that run between the hexagons and the dark roads that run between the triangles. Also note the loops, where starting from a hexagon, you can come back to it by only taking light roads. Similarly, for triangles and the dark roads. How many such loops exist for a given hexagon or triangle? Is there a light path from any hexagon to any other hexagon? Is there a dark path from any triangle to any other triangle? This piece is a mosaic of 3 exotic hardwoods. It is 17 inches in diameter and stands 21 inches on the base. I hope you enjoyed this video on the 2 beautiful mathematical sculptures by George Hart. In the next video, I will explore the use of mathematics in architecture. If you want to learn more about this topic, or in general just explore the use of mathematics in art, please read my math art blogs on Medium.